Okay, in this video, we're going to talk about a concept called resonance, all right? Resonance is a very, very important topic in organic chemistry, so we're going to take our time to to learn about this topic and look at a couple of different examples here. So resonance is a way of describing delocalized electrons within certain molecules or polyatomic ions where the bonding cannot be expressed by one single Lewis dot structure. All right. So what that means is when we talk about delocalized electrons, we're talking about electrons that are not shared just between two atoms. They're delocalized. They're shared between more than two atoms. Okay. This situation can arise for molecules or ions. Okay. And what that means is one Lewis dot structure doesn't accurately represent where the electrons are. So we have to draw multiple Lewis structures, and those are called resonance structures. All right. So a molecule or an ion that has these delocalized electrons is going to be represented by several or multiple Lewis dot structures, and we call these resonance structures. Okay. So each contributing structure will be represented by a Lewis dot structure. So what we really see here is that several Lewis structures are collectively used to describe the actual molecular structure. All right? And the actual structure is an approximate intermediate between all of the resonance structures, and that's called a resonance hybrid. Okay? These different Lewis structures, okay, the different Lewis structures are going to differ only in the position of the electrons, not in the position of the atoms. So basically, the atoms are going to be in the same position, but the electrons can be in different positions. Okay. Why this is important: electron delocalization lowers the potential energy of the molecule or ion and thus makes it more stable, okay, than any of the contributing structures. So when we have resonance structures, that's showcasing that these molecules are generally going to be more stable because we're spreading out the electrons or spreading out the charge. All right. Resonance is different from isomers, right? An isomer is a molecule that has the same formula but different arrangements in space, right? Remember, with resonance structures, our arrangement of atoms is going to be exactly the same, right? So in resonance, we're only differing by the arrangement of the electrons, okay? So a lot of kind of new terms here and definitions, and as we work through examples, hopefully these terms will make a lot more sense. All right. So when we talk about how we arrange electrons, right, we can really use arrows to show the flow of electrons. Okay, and we've spent a lot of time talking about mechanisms, right? So when we're drawing mechanisms of how reactions take place, the order in which bonds are broken and made, we use these arrows. So we're essentially using the same arrows we talk about with mechanisms, all right? But in this case, we're not doing a mechanism, we're just drawing different resonance structures, all right? So there are sort of three legal moves of resonance. There's three ways we can move electrons. Okay, the first is we can have a pi bond become a lone pair. So if you see in this example, we have a pi bond between 1 and 2. That can become a lone pair on carbon 2. Therefore, 2 has a minus and carbon 1 has a plus. Second thing we can do is we can have a lone pair become a pi bond, right? So here we have 2 electrons. We're now drawing an arrow in between carbon 1 and 2 to show that we now have a pi bond, all right? And then the next electron pushing we can do is we can move a bond. we can move a pi bond to form a different pi bond. So here I have a pi bond between carbons 1 and 2. That's now going to form a new pi bond between carbons 2 and 3. Okay? So let's look at a couple of examples here. We'll start with the acetate ion. All right. So what I'm going to do here is draw in our lone pairs because that's going to be important. If we look at this top oxygen, it has 2 bonds and 2 lone pairs. The oxygen on the right has 1 bond and 3 lone pairs, and that oxygen on the right has a negative charge. All right. So here we have one resonance structure, but that doesn't accurately represent the entire ion, right? Because it turns out that the negative charge is on the carbon on the right, but it's also on the carbon on the top. So we can show the flow of electrons. This lone pair here can form a bond, which forces that bond become a lone pair here. So if you look at our second resonance structure, this O now has only 2 lone pairs because the other lone pair became that bond. And then the O here now has 3 lone pairs because this bond here, right, became our third lone pair. And that is our second resonance structure. So you see in this molecule, I need 2 Lewis dot structures, 2 resonance structures to represent what it actually looks like, because our charge is actually being shared between both of these oxygens. All right? It's important to note we have to use a correct arrow. This double-sided arrow is used to represent that we have resonance structure, so that double-headed arrow denotes 2 molecules are resonance isomers, so it's not in equilibrium. It's telling us you have your resonance structures, right? And then what we can do is we can draw a resonance hybrid. So a resonance hybrid is kind of like a summary of these 2 resonance structures here, all right? And I just want to show you how that resonance hybrid is drawn. Right, what we do is we look at the sigma bonds first. So we know we have a carbon to an O and an O, right? And then what you'll notice here is, let me just clean this up a little bit, right? We notice in the resonance structure on the left, we have a double bond to the oxygen on the top, and in the resonance structure on the right, we have a double bond to the oxygen on the right. So we can represent those double bonds. Sometimes they have a double bond. So in the structure on the left, the O has a double bond, and the one it only has a single. On the left, it has a single. On the right, it has a double. So these oxygens sometimes are single, sometimes are double. So what we do is we just put dashed lines here, and that tells us that in one resonance, it's a single, and the other, it's a double, all right? And then what we can do here is we know that we have a single negative charge, right? So we can just put a minus in between these dotted lines to represent that there's a minus charge. I actually don't like putting that charge in the middle. What I like to do is say, put a partial negative charge on the atoms that have it. So if you see here in the resonance structure on the left, the O at the right has a minus. In the resonance structure on the right, the O on the top does. So we can designate that by writing a partial negative. So I'm writing a lowercase delta and a negative, okay? And this lowercase delta means that we have a partial negative charge, right? So I put a partial negative on the O on the top, a partial negative on the O on the right, and this is our resonance hybrid, all right? And this is kind of the best summary if we had to draw one structure on what it actually looks like. The O's are sharing electrons, they're delocalized, and the O on the top has a partial negative, and the O on the bottom has a partial negative. But it turns out it's actually easier for us to do mechanisms and understand this not really by drawing these resonance hybrids, right? So you're going to see we're really going to be, instead of drawing resonance hybrids, we're really going to be drawing our resonance structures, right? We're going to be drawing these as separate structures. Now, these are not separate structures that exist in time, right? These are two sort of forms that exist at the same time, but we're kind of separating them out so it's easier for us to see. There is only one structure, okay? But we're just drawing it in two different ways so we can sort of get a better view on where the double bonds are, where the electrons are, all right? So in this top example, we did this with an anion. We had a negative charge. Let's look at another example where we have a carbocation, all right? So here we have our carbons 1, 2, 3. You can see that we have a plus charge on carbon 1, all right? Carbon 2 and 3 has a double bond. So we can move this pi bond, this double bond, instead of being between carbons 2 and 3, to be in between carbons 1 and 2, which therefore leaves a positive charge on 3. So again, we have two resonance structures here. We use our double-sided arrow to indicate that. And then again, we can draw our resonance hybrid here, right, where 1 and 2 sometimes has a double bond, 2 and 3 sometimes has a double bond, and then we can draw our plus, right? Again, what I prefer to do is, when we draw resonance hybrids, to draw our dashed lines to say sometimes they're double, and then for the carbons that have the plus, I prefer to write a partial plus on the carbon on the left and a partial plus on the carbon on the right. Okay? So that's kind of our introduction to this. I just want to talk about some neutral molecules. We sort of have seen resonance structures before, or we've kind of encountered them. One is with a benzene ring, right? So if we take a benzene ring, here we have a double bond between, let me number our carbons, 1, 2, 3, 4, 5, 6. So the way this is drawn, it looks like we have a double bond, between 1 and 2, a double bond between 3 and 4, and a double bond between 5 and 6. But in fact, these electrons are actually all delocalized. So it's not like there's a single bond between 2 and 3. So we can always draw a resonance structure with any benzene ring. 1, 2, 3, 4, 5, 6, where in fact the double bond is between 2 and 3, 4 and 5, and 1 and 6. Right? So this is an example of how we can draw resonance structures with a neutral molecule. Right? Kind of another way we've seen this already is when we talk about some of our mechanisms. Right? So if we take an alkene here, and if you remember, we treat this with Br2, right? If you remember this alkene addition reaction, our pi bond can attack the bromine, break the bromine-bromine bond, and then we can add a bromine to one side, which forms a carbocation on the other, right? And what we said here is that this structure can be represented by two structures, whereby this bromine can have 3 lone pairs, or it can actually be connected to that other carbon via a bond. So we can kind of think of this as another resonance structure here, where now the bromine has a plus. So in one resonance structure, the bromine has a lone pair, and the other one is forming a bond to that carbon. So this is sort of another example on how we've kind of encountered resonance structures a little bit, all right? But really, the majority of the resonance structures that we're gonna talk about are really focused on conjugated systems. They're really focused on conjugated systems, right? So the majority of the time when we're talking about resonance structures, we're really talking about our pi electrons only. Our pi electrons only, all right? So I just kind of want to work through sort of our three examples, our three sort of basic examples. Here where we have a cation, okay? Another example where we have an anion, and then when we have a free radical, all right? So these are going to be simple examples, and what I want to do is just talk about the resonance structures. They're already shown here. And what I've done in this case, just to make sure we keep track of these, is I've included all of the hydrogens that we have, right? So we have 3 carbons, carbon 1, 2, and 3. So if you look at this first structure, excuse me, we have a double bond between 1 and 2. Carbon 3 only has 3 bonds, so that has a plus charge, right? So we can draw this resonance structure by moving the pi bond between carbons 1 and 2 to becoming a pi bond between 2 and 3. And here's the other resonance structure we get there. There's the electrons now between 2 and 3. The consequence of that is now carbon 1 has a positive charge, right? So when we talk about conjugated systems, we're really looking at our pi electrons, or electrons that are in p orbitals, right? We're talking about electrons that are in p orbitals. So you can see here I've kind of drawn in my p orbitals of my conjugated system. So in the structure on the left, I have 2 electrons shared between the pi bond on the left, and then the carbocation is an empty p orbital, right? And then we can move these electrons to be here, so our 2 electrons, our double bond is there, and then we have an empty p orbital here and a carbocation on the left, all right? And again, this is the same example that we kind of did up here, right? So if you wanted to draw the resonance hybrid, carbon 1, 2, 3, there's our sigma bonds, 1, 2, 3, right? Carbon 1 has a double bond on the left, doesn't on the right. 2 and 3 is just a single bond on the left, double bond on the right. So we draw our dashed lines here, right? And then when we look at our charge, in the resonance structure on the left, carbon 3 has a plus, and the resonance structure on the right, carbon 1 has a plus. So here we can just put a partial plus by carbon 3 and a partial plus by carbon 1, all right? So that's our allylic carbocation. And again, please note, as I move my electrons, when I move my electrons, I'm following the same rules as we move electrons with mechanisms. I always start where I have electron density, and I go to where I don't have electron density, okay? I start from where I have electron density to where I don't have electron density. Because with our carbanion, that's going to be a little different, all right? So if you look here again, this is sort of our simple examples. We have 1, 2, 3 carbons. Now we have a double bond between carbon 1 and 2, right? Carbon 3 is not a positive charge, it is a lone pair. So carbon 3 now has a negative charge, okay? So in this case, we have to start where we have the most electron density, and that's the lone pair. So this lone pair can form a new double bond between 2 and 3 there, which forces this double bond to become a lone pair on carbon 1 here. And that's the resonance structure we see with that. All right. If we look at sort of an orbital view of this, so let's draw in our orbitals. Okay. Again, we have a pi bond. That's a bond between two p orbitals. Now I have a lone pair, right? That's in a p orbital as well. So here, this lone pair becomes a bond between these two p orbitals here. That's that pi bond. And then this lone pair moves into that p orbital by itself here, right? So again, we still have our three p orbitals here. The p orbitals in green have the pi bond, and the one in blue, that p orbital in blue, has a lone pair, okay? And we can draw a resonance hybrid here. We have single bonds between carbons 1, 2, and 3. And if we look in the left structure, 1 and 2 has a double bond, and the right, it does not. In the left structure, carbon 2 and 3 doesn't have a double bond, but in the right one it does. So we can draw dashed lines between we can draw dashed lines between 1 and 2 and 3. And now we see that on the structure on the left, carbon 3 has a minus, and the structure on the right, carbon 1 has a minus. So now we're going to put a partial negative by 1 and a partial negative by carbon 3. And that would be our resonance hybrid. All right. So we've done carbocations. We've done anions, right? Carbocations, we move to the plus. Carbanions, we move away from the lone pair, away from the minus. Next, we're going to talk about allylic radicals. Okay, same system here, 3 carbons, 1, 2, 3, 1, 2, 3. Let's draw in our p orbitals, right? This is a conjugated system. Okay, so what we see in the resonance structure on the left, right, we've got a double bond, a pi bond between the p orbitals at carbon 1 and the p orbital at carbon 2. And now in carbon 3, we have a single electron in our p orbital, okay? So here when we designate our arrows, remember we're working with one electron, so we have to use a fishhook arrow. All right, we have to use a fishhook arrow. So in here, I'm going to take the electron from carbon 3. I'm going to take one electron from carbon from the pi bond to form my new pi bond here. And then the other electron in the pi bond is going to go right into the p orbital at 1 here. All right. So when we're working with radicals, we have to use our fishhook arrow, right? The 2 electrons of this pi bond, 1 comes from that electron, 1 comes from the electron here. The second electron goes into the p orbital by itself. All right. So we can draw a resonance hybrid for this. Again, we have 3 carbons, right? On the left, we've got a double bond between 1 and 2. On the right, a double bond between 2 and 3. So we can draw our dashed lines here. And now we don't have a charge, right? We have a radical at 3 or a radical at 1. So here we can't really write partial radicals, so we just have to, again, put a radical in the middle. All right, we have to put a radical in the middle. All right. Let's look at another example here because I want to talk about the fact that not all resonance structures are equal. All right, so let's look at a different molecule here. So now I have 4 carbons, 1, 2, 3, 4. Okay, 1, 2, 3, 4. we can draw a resonance structure of this. One, two, three, four. Remember, the position of the atoms doesn't change. Our sigma bonds are exactly the same, right? So if we look at our conjugated system, it's still only between carbons 1, 2, and 3, right? Carbon 4 is a methyl. There are no p orbitals here, right? We don't have any p orbitals. So that's not part of our conjugated system, right? 1 and 2 has a pi bond, 2 electrons shared between 2 p orbitals. Carbon 3 is a positive charge that is an empty p orbital, right? So to draw the resonance structure of this, I can take the 2 electrons between 1 and 2, move them between 2 and 3. That puts a double bond between 2 and 3. And then the consequence of that is carbon 1 has a positive charge, right? So if we draw in our p orbitals here, we still have our 3 p orbitals. In the resonance structure on the left, I've got a double bond between 1 and 2 and a plus at 3. In the resonance structure at the right, I have a double bond between 2 and 3, and then a positive charge, an empty p orbital at carbon 1. All right. So let me get rid of these. So what I want to do is now compare these structures. So we have two resonance structures, right? We could draw a resonance hybrid, but I'm not going to do that. But what I want to talk about is that these two resonance structures are not equal in terms of where the electron density is, right? So yes, the electron density is shared between carbons 1, 2, and 3. It's delocalized and delocalized. But one of these resonance is going to contribute more to the overall structure, all right? And the question is, which one? Well, if we look at this carbocation here, the resonance structure on the left, that is a secondary allylic resonance structure, right? Remember the term allylic. We have a secondary allylic carbocation. We have a carbocation that is allylic, right, to our double bond. The structure on the right is a primary allylic carbocation. So out of these two, they both exist, they're both present. Which one would be the more important contributor? That would be the structure on the left, right? Because it is a secondary allylic, while the one on the right is a primary allylic, all right? So if we drew a resonance hybrid here, right? 1 and 2 can have a double bond or not. 2 and 3 can have a double bond or not. We can still put a partial plus at carbon 3 and a partial plus at carbon 1. But the reality is this is not going to be 50-50, where you have half of a plus at carbon 3 and half of a plus at carbon 1, right? Because carbon 3, being secondary, would prefer to have the carbocation, right? So it's not going to be a 50-50 mixture. You're not going to have 50% plus at carbon 3, right? This might be more like a 20-80 or a 10-90. And the numbers aren't really important here. It's just understanding that this is the major contributor of the resonance structure, okay? And it's not that we can say it's more stable, right? Because this is only, again, one structure, all right? But we can say is that this carbon 3 will have more of the positive charge on it than carbon 1. And we don't really designate that. There's no way to designate that by writing it. But we just sort of need to know, because this is secondary allylic, that there's going to be a lot more positive charge at carbon 3 than there is compared to carbon 1, all right? So even though we can draw multiple resonance structures, it doesn't mean that they're equal in terms of where the electron density is. All right, so that's an important concept for us to understand. There's sort of, the electrons are shared and they're delocalized, but they're not delocalized 100% equally. Okay, so let's just do two more examples. Let's see if we can draw the resonance structures for these two structures here. All right, and these are a little more complex, right? So for the first one, we have an anion. Okay, that's kind of important because we know we have to move from electron density. So what I like to do is I like to just draw in my p orbitals because we're going to be moving electrons through our p orbitals only. We're not going to be touching the sigma bonds, right? So we know we have a pi bond, that's 2 electrons between 2 p orbitals. I have a lone pair next to a pi bond, that's in a p orbital, and then I have another double bond here, all right? So that's where the electrons can flow. So our electrons in this structure are only going to be able to move, our pi electrons, our conjugated system, are only going to be able to move through these 1, 2, 3, 4, 5 bonds. All right, so if we kind of erase that, what I'm going to do is I'm just going to highlight here that as a p orbital, here, here, and there. Okay. Remember, like this carbon here is sp3 hybridized. It's got 2 hydrogens. We're never going to form a double bond or anything else there. Not going to contribute. So we're just going to be moving electrons through the highlighted system. All right. So it turns out here our lone pair is in the middle. Because it's an anion, we're always going to start moving our electrons at the lone pair. And there's really 2 options. I can take the lone pair, form a bond, a pi bond to the left, which then pushes this pi bond to reside on that atom by itself. So let's draw that resonance structure. I draw my sigma bonds exactly the same. And now we're just moving our electrons. So you'll see that this lone pair became a double bond. Let's draw that here. This double bond became a lone pair. Let's draw that here, right? And we didn't touch the double bond at the O, so that remains a double bond, all right? That O still has 2 bonds and 2 lone pairs, right? The consequence of moving these electrons is now this carbon, right? This carbon here now has 5 valence electrons around it, so we have to make sure we put a negative charge on that carbon. Okay, that's our first resonance structure, right? So I've moved, lone pair became a bond there, bond became a lone pair here, all right? Now we can do another resonance structure, and I'm going to do it from the same one here. I'll use different colors. We'll use green. So instead of the lone pair going to the left, the lone pair can go to the right. This lone pair can form a bond there, and then that bond can form a lone pair on the O. All right? So we draw in all of our sigma bonds. All of our atoms. We didn't touch this here, so that's going to remain. The double bond remains there, but now the consequence of taking this lone pair and forming a bond means we now have a double bond here, right? And this double bond here has become a lone pair on the O. So the O had 2 lone pairs, and now the O has an extra lone pair, which means the O now has 7 electrons around it. Let me just move this a little out of the way, right? So there's the lone, oops, let's go back. Let's make that, again, green. our extra lone pair is green, and that means that the O has a minus charge here. Okay, so these, we now have a total of 3 resonance structures, right? The one we started with, and then we've drawn 2 other resonance structures here, all right? So this anion has 3 possible resonance structures. A question for you, what would be the major contributor? What atom would tend to have the most electron density, the most partial negative charge around it, right? So if we kind of evaluate these, right, here we have a carbon with an extra lone pair and a minus. Here we have a carbon with an extra lone pair and a minus. Here we have an O with an extra lone pair and a minus, right? All of these structures have full octets, full octets, full octets. So which of these would be the major contributor? Well, here we can think about electronegativity. Which atom is more electronegative, carbon or oxygen? We know it's oxygen, which means oxygen would prefer to have the negative charge, all right? So if we look at these structures, right, this one here is going to contribute more to the overall structure. Again, this is one structure, right? There's one structure here, right? We can draw a resonance hybrid to show that. Dot, dot, dotted lines, O. We have a partial negative, we have a partial negative, we have a partial negative. So which atom is going to tend to have the most minus charge? The O will have the most electron density, the largest partial negative, right? Because the O is electronegative, is more electronegative than carbon. So this is sort of the major contributor, all right? Let's look at sort of our another example here where we have a carbocation, okay? Again, I'm going to draw in my p orbitals. Okay, so we have an O with 2 lone pairs, right? A pi bond, 2 electrons are shared between 2 p orbitals. A positive charge is an empty p orbital, right? And remember, anytime we have a lone pair next to a p orbital, that's part of our conjugated system. So one of these lone pairs is part of the conjugated system, all right? Please note that these 2 carbons over here have 2 H's, right? There's no p orbitals here. Those are sp3 hybridized. So these are not going to participate. Those cannot have a plus or not have a double bond, right? Because those are sp3, all right? So if we kind of get rid of the p orbitals and just highlight where we can move our electrons, here, here, and here, we see we have sort of 4 atoms on where we can move electrons. All right, so let's see how we can show the delocalization, how we can move our electrons. When we have a carbocation, right, when we have a carbocation, this is lacking electron density, so our arrows need to always move towards the plus, right? The positive charge is short on electron density, so we always have to move towards it, all right? So what can we do here, right? I'm just going to move the electrons kind of one at a time. What we can do is I can take this double bond and I can move it between those 2 carbons there. That's our first resonance structure. So let's draw in our sigma bonds. We haven't touched the O or the lone pairs on the O, right? This double bond is now moved here. Let's draw that double bond in there. The consequence of that is this carbon here now has a positive charge. Right? Just remember there's 1 H here, 1 H here, and only 1 H there. Okay? So we still have 1 H, 1 H, and 1 H. So that carbon only has 3 bonds and has a positive charge. Okay? So we always have to remember how many H's we have, but we don't have to really draw those in. So I'm going to just get rid of those H's on our resonance structure. right? Because we don't have to draw them in, but we have to know that they're there. So there's our first resonance structure, okay? What do? We can kind of continue on. I draw my double-sided, okay? Look at our highlighted system, all right? So what we see now is that we have a lone pair, all right, next to a plus. So what else can we do, right? This lone pair can actually now form a bond between that carbon. And that will get us our last resonance structure here, all right? So what we're doing is this lone pair is now going to form a bond, all right? So let's have that lone pair form a bond here. We haven't touched that, so that still has a double bond, and that's the structure that we get. What do we have to remember, though? What's the consequence, right? If we look at this oxygen here that has 3 bonds in one lone pair, that only has 5 valence electrons, so we have to make sure we have a plus charge on that O, all right? So these are all the resonance structures we can form, okay? We can draw our resonance hybrid, and generally speaking, when we draw these, we're not going to be drawing our resonance hybrid, okay? So I'm drawing dashed lines because that sometimes has a double, no double, double, double. Here has a double, doesn't have a double, doesn't have a double, does, right? So I draw sort of my dashed lines here. Dash sometimes has a double, sometimes has a double, sometimes has a double, right? And what do we know? This carbon has a partial plus, that carbon has a partial plus, and the O can also have a partial plus. So that's our resonance hybrid. And again, what would be the major contributor here? Let's evaluate these, right? If we look at this resonance structure here, what we notice about this carbon is it doesn't have a full octet. That's not great. If we look at this resonance structure here, this carbon doesn't have a full octet. Not great. But in this resonance structure, everything has a full octet. So even though oxygen is more electronegative, this would be the major contributor because every atom has a full octet. And that's sort of more important than electronegativity. Which means if we think about these 3 carbon atoms having positive charges, right, the O is going to tend to have more of a positive charge on it rather than the 2 carbon atoms, right, because that's when it has a full octet. That is the more important contributor to the resonance structure, all right? And I'm just drawing the resonance hybrids just so we can sort of understand what the molecule looks like. Remind you that this is only one intermediate, but we're just drawing 3 different resonance structures to sort of represent it. All right? So that's our lesson on resonance.